Is it okay like that?
It's a bit better, but with F5, with the key F5, F5.
The problem is if I put full screen, do you see it?
No.
When you share the screen in Zoom, you have to share the full desktop, not only the application.
Yes, that's what I did. Yes.
The full desktop.
And so, how is it? So, what do you see?
All the slides.
Also, just the main window of PowerPoint.
Yeah, but okay, so that's fine, no?
Okay.
Okay.
Yeah, okay. So, we'll be talking about AGNs in Gaia alerts, but also coming from ZTF or other surveys, and particularly changing look quasars and how we need ground-based follow-up and SVOM follow-up. I will pass quickly on matching previous alerts. Just look the last line we found in matching with surveys, mainly cataclysmic variables, AGN galaxies and 100 quasars, among them changing look quasars. So what we are doing now is variability is a good way to identify new AGNs or QSOs. The Gaia alerts provide candidates like ZTF also. And so we are searching for archive spectra and getting new spectra to characterize what is going on. The problem is that the spectral in the archive or the follow-up is usually different from the alert date. And to understand what is going on, we need to minimize the delay between the alert and what is done from the ground-based. And as the previous speaker said, with LSST coming, selection is crucial to reduce the number of objects to be followed. So what is a changing look AGN or quasar? It's a cipher2 or a liner which is suddenly
Excuse me, Michael, you are in the first slide on Jet.
You don't see the next slide?
No. Could you stop sharing and share all your screen, please? Maybe
Yes,
that's the
okay.
problem, not only the app of PowerPoint.
Yeah, yes, that's what I did, in fact. But okay, let me just. Okay.
Do you have two screens, Michel?
Yeah.
Yeah, that's the problem. When you have two screens, probably you were showing the wrong one.
Okay, so I stopped sharing screen. And now what is happening?
I think you have share again.
Yeah.
And put in full screen.
Mm-hmm.
Yes, so you're sharing your second screen, basically. That's the problem.
What you mean by second screen? Sorry for
that. The best is if you click on the slide instead of going full screen, just stay on PowerPoint and
okay, yeah.
Click on slides. That will be easier.
Yes, okay.
Thanks.
So is that, do you see it now?
Yes, we see what is a changing look AGN
yeah, okay, yeah, good. That's the point. So it's a cipher2 or a liner which suddenly shows broad lines, or the reverse, the broad lines are disappearing. And until recently, only few cases were known. I show one example, NGC 7582, which you see on the figure. In the course of 1 year, the broad line H alpha here on the right appeared, and a few months later disappeared. And now today, with the old sky surveys going on, we see many new examples of that kind, but we need a better time sampling to understand what is going on. And I will show you a few examples of other similar examples. For instance, this is a case alerted by Gaia in June 22. the STSS reference spectrum at the bottom is a liner, and the new spectrum obtained after the alert shows clearly H alpha and H beta broad component. So the question is, what is going on? Is it simply an increase of the accretion rate or a change in the reddening or what else? And now we have many examples of that kind coming from the Gaia alerts. This is an example which has 3 archive spectra within 1 month. So you see the broad MG2, the MG2 increasing and the H beta broad here increasing also. And down is the light curve. The red point here is where the spectra were taken. And you see this object is evolving with time. And the latest spectrum on the left, corresponding to the last photometric point, is again in the high state and shows magnesium 2 and broad H beta. So the 2 objects on the top are classical variations in quasar, which are probably changes in accretion. These are not the ones we are interested in. We are more interested in those which show a long-term variation here, increase over 2 years, and you see the bottom also. So what is changing there? Just using the light curve is not enough. These are 2 cases where we missed the burst to take a spectrum, but there are other cases where you see long-term change, increasing or decreasing, and that's what we are trying to understand. So this is one example of those long-term increase. The reference spectrum doesn't show much H beta, and the recent spectrum obtained at the Nordic Optical Telescope shows clearly broad components appearing. Other example of the same kind, reference spectrum on the top, which shows very small narrow component, and the broad component is then increasing with time. I'll show you many of those. This is an interesting example, which is a classical thing. Initially, it's a liner, and when the broad component appears, at the same time, a strong blue continuum appears also. I can show you many of those. I'll just go quickly. So how does one explain that? If you take the classifying, the standard unified model by Uri and Padovani, you suppose you have an obscuring torus here. The broadline region is in the center, and depending whether you look from a high inclination where you see inside the torus, you see the broad lines, and if you observe the line of sight through the torus, you don't see the broad lines, only the narrow lines, and that's a CIFAR2. But with a system like that, there is no possibility to change between 1 and 2 by changing the viewing angle. No? So what we need is to measure the time scale of changes between the photometric change and the spectroscopic change and try to understand. So here I show recent models by the group in Mexico City, Deborah Dulcin and colleagues. On the right side, you have 4 models of CIFAR1s, and on the left side, 2 models of CIFAR2s, which are all based on real close-by CIFARs, which could be observed into details. The gray is the gas which is producing the X-ray, and the brown is the dust which is producing the infrared. And you see different models depending on the type of objects you observe, where the gas is either uniform or in clumps, and the same for the dust, either uniform or in clumps. And the lower right scheme is the classical one of a CIFAR1, where the line of sight is the red line here. You see directly into the broad line in the center, while on the left, it's a CIFAR2, where the line of sight is going through the torus and the dust, and therefore you do not see the central broad line. So the important point is there is a diversity of situation in known CIFARs. If you use the infrared that measures the dust, which re-emits the UV continuum coming from the central accretion disk, and the gas in gray is the one producing the X-rays. So if the gas is uniform, like in this model, you do not expect to see variations in the X-rays, While if the gas is in clumps, like here, you do expect to see variations. And you see in the two top figures, on the right top is a Seifert-1, and on the left top is a Seifert-2. There is not much difference in the model between this Seifert-2 and this Seifert-1, except that the viewing angle of the torus is much larger. So when it's only in a case like that that you can expect variations between 1 and 2 if the clumps are moving in Keplerian orbit around the center, and then from time to time there's a hole and you see through the center and the broad lines appear. So that's the interpretation, but you have no idea of the time scales and of the size of the clumps. So we need multi-wavelength follow-up, as I said, X-ray to measure the gas column density, and variability, because that tells you whether it's clumpy or not, and their SVOM will provide that. And so the idea is that with the pointings of SVOM, either through GRBs or on a separate program, we should monitor a set of known AGNs and see what we see for variability. And with the field of view of Eclair, as I asked before, you have a good chance to see much more than one AGN at a time. For the ground-based follow-up, you need any telescope, say, larger than 2 meters to do spectroscopy. I show here the new spectrograph at Haute-Provence. In principle, Christophe Adami is supposed to tell you the details about that, so I will not insist much. But I want to show you my conclusions. Say, we have a lot to do in spectroscopy. We need a lot of spectroscopic time. For spectroscopy, I'm afraid the colibri is not enough. We need at least a quetzal or maybe even an eagle. But the colibri will help to fill in the light curve, because the Gaia follow-up or the ZTF follow-up is only scarce once every 3 days, or for Gaia it may be sometimes 30 days until you get the next point. So the colibri will fill in the light curve to see the general trend. Spectroscopy we can do in Haute-Provence, with the Liverpool telescope or a larger telescope at ISO, the X-ray with SVOM. And the interesting thing, I hope we could get collaboration from the UNAM group for the models they have started to develop. So, muchas gracias para su atención y ojalá que todo le vaya bien en ese periodo difícil de pandemia. Gracias.
Gracias a ti, Michel. Any questions? Please raise your hand. Okay. We have not questions. Thank you again, Michel.
Alan is.
I'm sorry. Alan, please.
Yes.
This is a classic. This is not a question, it's a comment. I just say that we are considering making a spectrograph a little bit like the Mistral spectrograph for Colibri, but I wouldn't hold my breath for it being ready soon.
Yes, on the other hand, from my experience, 1.3 meter is a bit small to do spectroscopy of 18, 19th magnitude objects. Maybe there are a few cases where the object is brighter, so we could do that. But we have to coordinate and try to get spectroscopic time at other telescopes.
Yes, definitely.
Okay, more questions?